Bismillah ar-Rahman ar-Rahim. I am Bushra Al Muhammad. I'll talk about impression materials, part 1, and our reference is Richard Van Noort from page 137 to 154. Impressions is a detailed replica of the teeth and the tissue of the oral cavity. From this replica or impression, a model can be made that is used in the construction of full dentures, partial dentures, crowns, bridges, and inlays. Impression materials can be classified in terms of rigid and elastic impression materials. The rigid impression materials cannot engage undercut that may be present on the tooth or the bone, so their use is restricted to a edentulous patient without bony undercuts. The elastic impression materials are subdivided into hydrocolloid and elastomeric impression materials. Both are able to engage undercuts and may be used in edentulous, partially dentate, and fully dentate patients. The important characteristics of impression materials can be identified from the point of view of the patient and the dentist. For the patient, we need a neutral taste in the door, short sitting time, small tray, easily removed, and of course non-toxic. For the dentist, we need it to be easily mixed, short working time, easily removed, good quality impression, low-cost materials, and easily disinfected. Another requirement of an impression material is the accurate reproduction of surface detail, and this depends on the viscosity of the mix and the ability of the impression material to adapt closely to both the soft and hard tissue. So low viscosity is therefore desirable. Please refer to page 137 for further important details. Another requirement is the dimensional accuracy and stability, and this depends on few factors. First is the type of tray. If the tray is prone to distortion, the resultant model poured from such a tray will also be distorted. Hence, highly flexible tray should be avoided, and a good bond between the tray and the impression material is very important. Otherwise, it will distort the impression. The second factor is the shrinkage. When the impression material sits, it will result in some shrinkage, and this will increase the space previously occupied by the hard or soft tissue, and the result is a die which is slightly larger than the original tooth preparation. For the thermal contraction, ideally, the impression material should have a very small contraction, less than 0.5%, and this will result in the production of a crown that is slightly larger to compensate for the cement that will be used later. The fourth factor is the permanent set. The impression material must be sufficiently flexible to allow removal from the undercut regions without causing distortion. Storage stability. There is usually a significant delay between the taking of an impression and its arrival in the dental laboratory. It is important that the impression material neither shrink, expand, nor distort during this time period. Impression technique. In the case of silicone impression materials in particular, there are a number of impression techniques that can be employed. It is important that the appropriate technique is used for each material. Zinc oxide eugenol is a rigid impression material that is used for edentulous patients. These are impression compounds that are made from wax and come in a form of a wax sheet. This is an example of a rigid impression compound that is used for edentulous patients. This is an alginate impression material. It's elastic, irreversible hydrocolloid. This is a polyether impression material. It is expensive material and comes in an automatic mixing machine. Polyvinyl siloxane is available in an automatic mixing machine and a manual mixing gun. The first elastic dental impression material was the hydrocolloid, which was introduced to dentistry in 1925. Since then, many elastomeric impression material have become available. A colloid has a glue-like physical character. A colloid is a system between a solution and a suspension. A solution is a homogeneous mixture consisting of a single phase. A suspension is a mixture of two distinct phases. A colloid is a heterogeneous mixture of two phases, where the two phases are not readily differentiated. The difference between a colloid and a suspension is that in a colloid, the disparate phase is not readily detectable microscopically. If the particles are suspended in water, the suspension is called a hydrocolloid, with the liquid being a hydrosol and the solid being a hydrogel. Examples of hydrocolloid impression materials are agar, which is reversible, alginate, irreversible. Agar is a galactose sulfate, which form a colloid with water. It liquefies a certain degree and gel at certain degree as well. Alginates are based on alginic acid, which is derived from a marine plant. Reversible hydrocolloids can return back to its original state. In order to use agar, you should have an agar conditioner. It consists of 3 compartments. One contains water near its boiling point and it is used for liquefying. Second is kept at 63 to 66 degrees Celsius for storing the agar. The third compartment is kept at 46 degrees Celsius and is used for tempering the agar after it is placed in the special water-cooled tray. This compartment is necessary to ensure that the agar is cooled at a temperature that the patient finds acceptable and it will not burn the tissue. Hydrocolloid must be cast as soon as possible or kept in 100% relative humidity for 1 hour maximum by wrapping in a wet towel. Cast must be separated from impression promptly. Hydrocolloids are dimensionally unstable in storage. They are subjected to shrinkage, evaporation and syneresis, imbibition, absorption of water, causing swelling and expansion of gel. Syneresis is the shrinkage that occurs due to the loss of water and salt that forms as an exudate on the surface of the gel. Hydrocolloids are viscoelastic. The elastic behavior is responsible for the rapid deformation. The viscous behavior is responsible for the slow deformation. Since hydrocolloids are highly viscoelastic, they should be removed with a quick snap to be elastic. The strength depends on the rate at which the impression is removed. Higher rates result in higher compressive and tear strength. Hydrocolloids are stronger when they are deformed rapidly. Alginate is an irreversible hydrocolloid which can't get back to its original state. These are some brand names for alginate. This table shows the composition of an alginate impression material. We have sodium alginate, 18%. It is used as an hydrogen former. Calcium sulfate dihydrate provides the calcium ion for the cross-linking reaction that converts the solution to gel. Sodium phosphate, 2%, controls the working time. Potassium sulfate, 10%, controls the setting of the model. Fillers, 56%, controls the consistency. Sodium silicofluoride, 4%, will control the pH. When you mix alginate with water, a chemical reaction occurs. And this reaction is irreversible, so that's why the material will be used only once. The setting reaction of alginate consists of retardation and gelation. In the retardation, the working and setting time is determined by the rate of release of calcium ion. Rapid dissolution of the calcium sulfate would give the material inadequate working time. So in order to overcome this, we added sodium phosphate in order to regulate the initial burst of calcium. So in the retardation, sodium phosphate works as a retarder. Alginate is subjected to permanent deformation, and it will increase when the impression is removed too soon or removed slowly, or it was held under compression for a long time and the water to powder ratio is increased. If you need to extend the working time, you should use cold water. This table is a comparison between the regular and fast-set alginate. The mixing time in minutes for the regular is 1 and fast-set 0.75. The working time for the regular is 3 to 4.5. The fast-set 1.25 to 2. The setting time for the regular 1 to 4.5. The fast-set 1 to 2 minutes. In order to disinfect alginate, first you need to rinse thoroughly in tap water for 15 seconds. Next, spray the disinfectant, then rinse, and finally place it in a sealed plastic bag and send it to the lab. Next, spray the disinfectant, then rinse, and finally place it in a sealed plastic bag and send it to the lab.